All right, so here we're going to start 15.4. We're going to be doing double integrals in polar form. Thankfully, it's not too bad, and it actually can let you solve some integrals and stuff that you wouldn't normally be able to solve, or at least not very easily. So the basic idea here is to find an infinitesimal little element of your area, and then integrate and add those all up. And you can see here in this picture, they're basically showing a little element of it, a little teeny there. If there, it's in orange. And you can see that, we have some change in theta, and we also have some little step in the radius in r for some little area. And that would be true at any one of those that we go. So we now have to turn those into actual lengths, because delta theta itself is not a length. Delta r is, but that delta theta is not. So we can't just integrate over it and get an area, because delta r times delta theta is not an area. So we come here to this picture, which is an okay picture if you like it. I prefer really just kind of, I don't know, I always thought it was a little more straightforward, because in my version of it, your little area, if we have some place like this, if I'm looking out at it like this, and I'm looking at some little aerial element right here, then I would look at this and say, all right, well, I have a little step here, dr, that I'm stepping up that way. And then I have a little step this way, it's delta theta. And as I talked about before, when I did that problem where we calculated the volume of a sphere, that d theta is not a length, because depending on where we are, that d theta, that little step we're doing for our different aerial elements, is going to be different in size. And if you go out way further, it's going to get larger, that d theta step. So d theta itself cannot be that step. Instead, we have to take essentially what is the arc length. And the arc length of a step like that, when you rotate an angle, is actually r times theta. So this would be r times our change in theta. And that right there would give us an aerial element, r dr d theta, those things multiplied together. That right there is a tiny little area right there in polar coordinates. So r dr d theta. And that's essentially what they get through. They're just using delta thetas and delta r's instead. But again, it's an r delta theta, and that's your delta A. So, whichever way you want to think about it, if you like it their way, go with their way. If you like it my way of thinking, then go with my way, and you can do it. So it's pretty simple from there to find then the limits of integration. You're going to do, it's very similar to what we've done before. You're going to look at when do you enter and exit the function. And then you also have to look at what angles you're going through. So if you look here, you can see that the smallest angle that you're starting at is pi over 4. That's this angle right here. And then it's rotating on around to pi over 2, the largest angle you go to. So that's what you're going to integrate theta across, what angle you're actually traversing. And then up here, you're going to do something similar to what was done before, and you're going to look at where you enter it, where you enter the function, and here you're entering it at square root of cosecant theta at r equals x, and then you're exiting at r equals 2. And so just by doing that, you can get your limits of integration, and then you just go through and integrate it with dA being r dr d theta. All right, so I'm going to pause this real quick and check for any questions. All right, so then continuing on, we can take a look here at an example. First, what we're going to do here is find the limits of integration for integrating f as a function of r and theta over the region r that lies inside the cardioid 1 plus the cosine of theta, and outside the circle r equals 1. There's a picture of this on the next page. So first you sketch the region. There it is. And label it. So you can see the cardioid, and you can also see the circle. And then you're interested in, when does it enter? Where does it exit? You can see that the area between them, this whole area here in this light blue, it starts down here at negative pi over 2 and then rotates all the way around to pi over 2. So that's going to be our integration limits for theta. And then as far as r goes, you can see we're entering into the region we're interested in here at r equals 1, and we're leaving it at r equals 1 plus cosine of theta. So that's what our limits of integration will be. So the limits for r are from 1 to 1 plus cosine theta, and then the limits for theta is negative pi over 2 to pi over 2. And so then you would just go through, you would replace your dA with this r dr d theta right there, and then you would do the integral based on what the function was that you were given. So similar to what we were doing before with dx and dy, except you have to multiply this r into it rather than just leaving it. Okay, so quick little pause and see if there's any questions on that. All right, so then continuing on after we did that, let's take a look here at just the general formula for area of a closed and bounded region R in polar coordinates. So again, it's just like before, where our function that would go here is just missing or it's equal to 1. We're not doing that extra integration that we would have done previously to get the values of it. In fact, it probably would have been more like cylindrical coordinates here, where we would have had like an integral, an integral, an integral, and then a r dz dr d theta, something like that, to take our first step and get f of r theta in there. And it would have been like from 0 to f of r theta. So we're not gonna, if we take that step out of it, just like we did previously, we're left with just the area. And so we can find the area of something just by doing that. Or the way the book explained it was just letting the function that we're integrating over the area equal 1. All right, and so let's take a look here at this example. This is r squared equals 4 times the cosine of 2 theta. And so what I'm going to go ahead and do is give you a chance to try and set this one up and find the area. Look at when it enters, when it exits. You can look at the picture to see what your limits of integration should be, and then go ahead and give that a try while I pause this. All right, so here's that example. If you're watching this later, just pause it and go through it, but it's pretty straightforward. Then we come over here, and this is a nice little changing Cartesian integrals into polar integrals. You do your substitution of x equals r cosine theta, and y is r sine theta, and then you swap out dx dy for r dr d theta. That's your, this is dA over here, this is your dA over here, your little area element right there. And so as long as you do that, it actually becomes pretty straightforward. This is usually pretty useful whenever you have an x squared plus a y squared in your function, and you make this change, and it actually simplifies down a lot of times. So let's take a look here. I meant to clear that off before I showed you. So let me do this real quick. We'll pretend it wasn't there. And so when we look at this here, we have e to the x squared plus y squared dy dx. Anybody that wants can go ahead and just try to do that integral, but you will find it is not at all trivial. It is actually a very difficult integral to do. However, if you make the substitution as shown on the previous page and convert this to a polar coordinate integral, it actually becomes a lot simpler. So what I'm going to go ahead and do here is pause this for a moment and let you have a try at that. All right, so there's the answer for that one. Pretty straightforward integral after you do it and go through and get this answer down here. Okay. After that, here's another one. And I'd like y'all to go ahead and try this one now. It should be a little simpler than the last one maybe, but go ahead and give it one more try. That was a short recording.